So let's continue on with the experiments. In the last video, we talked about the 3 experiments that led up to quantum mechanics, and that was the double slit experiment, blackbody radiation, and the photoelectric effect. Let's discover some of the things that were the big ahas. In the Young's double slit experiment, that was implying that light had wave functionality, whereas the photoelectric effect showed that light actually acts as a stream of particles. This introduced the concept of wave-particle duality, which means things weren't no longer having to be in one category or the other, but actually matter could have both properties of a particle and as a wave. Based on these 2 experiments, light was acting like both. Later on, we're going to see how the electron is also the same. So let's review some of the equations that we've learned. The first equation that we learned was the light equation, and that is the speed of light is equal to wavelength times frequency. We also learned that we could calculate the change in energy of a particle by knowing Planck's constant times frequency. If we were to combine these 2 equations together, we could actually get that energy is equal to Planck's constant times the speed of light over wavelength. Remember that Planck's constant is 6.626 times 10 to the negative 34th joules second, and that energy is measured in joules. This video right here is a video that will help explain some of the important information about Young's double slit experiment and the photoelectric effect. I may have linked this before, so if it is a repeat video, you don't have to watch it again, unless you want to. Could be fun. Alright, let's do some examples. Example 4 and 5. Example 4 asks us which photons have higher energy. Light from a red stoplight, which would have a wavelength of approximately 750 nanometers, or yellow light with a wavelength of 600 nanometers. So this question is not asking us what the energy is, it's just simply asking us which photon would have the higher energy. So this question you could solve by mathematically figuring out what the energy is for both red light and yellow light and then comparing. But a better way to solve this problem actually could be using our properties to figure out our math relationships to figure out which one would be the one that has the higher energy. Remember, if we're looking for the one that has the higher energy, that's the same thing as saying we're looking for the one that has the higher frequency, which is also saying the one that has the smaller wavelength. And based on that relationship, which one has the smaller wavelength? 600 nanometers, which belongs to the yellow light. So yellow light, photons from yellow light have higher energy than photons from red light. And that solves the problem. Now let's look at example number 5. Example 5 asks us, what is the wavelength of a radio station's waves that is transmitting at a frequency of 101.5 megahertz? Additionally, what is the energy of this light wave? So let's first solve for wavelength. So I want to figure out what wavelength is, knowing that frequency is 101.5 megahertz. And if you didn't notice, that's actually a radio station. Radio stations, when you tune in your car, are always in megahertz. So in order to do this problem, we'll need to be able to convert from megahertz to just hertz. But nevertheless, we're going to solve this by using our light equation, C equals wavelength times frequency. Or I could rewrite that as wavelength is equal to the speed of light divided by the frequency. And so, plug in my value for the speed of light, 2.998 times 10 to the 8th meters per second, divided by my frequency. Now my frequency is 101.5 megahertz. But we could do the same thing here that we did with nanometers. What does the prefix mega actually stand for? Mega stands for times 10 to the 6th. So if I just add on times 10 to the 6th, I have now converted it to just hertz. As a result, the seconds will cancel with the hertz, because remember that's 1 over second, and my length will be in meters. And so let's calculate. 2.998 E8 divided by 101.5 E6, and I end up getting, with 4 sig figs, that the wavelength should be 2.954 meters. Now, is there any reason to convert this to nanometers? No, because we weren't converting for a wavelength in the visible light region. We were converting to a radio station's waves, which, remember, radio station waves or radio waves are very long. So it wouldn't make sense to convert this to another unit other than meters. So we're going to keep it just as it is. Now, we still need to solve for energy. And so energy is going to be calculated. And let me just put it down here. I'm going to choose black ink so it shows up a little bit better. There we go. Energy can be calculated by taking Planck's constant times frequency. And so Planck's constant is 6.626 times 10 to the negative 34th joule seconds. And my frequency was the 101.5. Remember, I have to have it in times 10 to the 6th hertz, or I'll write 1 over second. So you can see that the seconds cancel, and my answer will be in unit of joules. And I'm going to write the energy up here because I'm running out of space. But I'm going to calculate that by just multiplying those two numbers together. 6.626 e negative 34 times 101.5 e6. Keeping 4 sig figs for my answer, 6.725 times 10 to the negative 26th joules. And that would be the energy of that particular radio wave. Let's do one more. Let's calculate the energy in kilojoules this time of a photon of light that has a wavelength of 5.00 times 10 to the 4th nanometers, which, just so for your information, is in the infrared region. All right. So energy is equal to Planck's constant times frequency. The problem is I don't know what frequency is. Frequency is not in this problem at all. But using the light equation, I actually know that frequency is simply the speed of light divided by wavelength. And so what I could do is I could substitute frequency for what I know is equal to frequency, which is the speed of light over wavelength. And this is how we ended up getting that equation a few slides ago. So energy can be calculated this way if we know the wavelength instead of the frequency. And so I'm going to solve this by plugging in h, which is Planck's constant, 6.626 times 10 to the negative 34th joule seconds, times the speed of light, 2.998 times 10 to the 8th meters per second, and then divided by my wavelength. Now notice my wavelength is in nanometers. I need to convert that to meters. Let's do the same thing that we did before. So write the number that's given, which is 5.00 times 10 to the 4th. And so it's nanometers, but what does nano stand for? Nano stands for times 10 to the negative 9th. So if I add on times 10 to the negative 9th, I have now converted it to meters. Well, obviously, we don't want to leave this, right? So let's simplify that. What would this power of 10 be if we were to simplify it? Remember our properties of when you multiply powers of 10 with exponents, we would just simply add these exponents together. So 4 plus negative 9 would actually simplify all of this. Whoop, don't want to delete too much. Whew. All of that would just simply be 5.00 times 10 to the negative 5th meters. And so that was just a metric conversion. So now we have my wavelength in meters. And so before we do any of the math, let's just remind ourselves that the meters will cancel, the seconds will cancel, and I'll be left in joules. Now I'll have to convert to kilojoules, but let's figure out what the joules is first. 6.626 e negative 34 times the speed of light, 2.998 e8, and then divided by 5.00 e negative 5. And it looks like I need to keep 3 sig figs, and so my answer would be 3.97 times 10 to the negative 21st joules. But I have to convert this to kilojoules, and so I'm going to do a metric conversion. To go from joules to kilojoules, I know there are 1,000 joules in 1 kilojoule. And so that would make my answer 3.97 times 10 to the negative 24th kilojoules. All right, that wraps up section 2. We'll see you in section 3.